Well, good morning, everyone. I'm Alba Garzon Manjon. I'm from the team of Institute Catalog of Nanoscience and Nanotechnology, and we are in charge of the task 5.2, like Marcelo was explaining. So today, I would like to give you a really brief introduction, a summary about photocatalytic materials, specifically for CO2 reduction, and I will show you two more examples in another applications, and also explain you a little bit about this state-of-the-art focusing on in situ microscopy. So for the introduction, I wanted to explain you why is important this in situ microscopy. So imagine you want to produce your catalytic materials. You go to the lab, you can prepare your single atom catalyst or your nanoparticles, your 2D materials, and then you have them. So you check the properties. In this case, I make the scheme for CO2 reduction, and you have a specific behavior. So then you come back to the lab and you change some parameters. And when you characterize them again, the behavior, these catalytic properties change, and you don't know exactly why. So in order to correlate the synthetic properties with the synthetic process with the properties, it's really important the characterization, and more specific in situ characterization, because here you can see how your reaction is developing in life. And at the end, seeing is believing. Right now, we have several challenges. For example, new materials are coming, so we need to adapt this characterization process to these new materials. The in situ experiments are not easy, as you will see in my next slides, because also it brings a lot of data that maybe the reaction happened in 1-2 seconds, and you have a record of 2 hours. So to process this data is challenging. The sample size, we need to adapt the sample of these catalytic materials for the TM, for synchrotron, as Paolo was explaining, and also these characterization techniques are having quite challenges. And at the end, to make all the correlation between all the characterization, material, synthetic process, to understand exactly the behavior of your material. So for the in situ and ex situ TM, you first can understand the chemical parameters of these nanomaterials. So you can visualize the morphology, the size, the composition, how these nanomaterials is organized, which is the crystallinity. You can also have them in different states, changing concentration or in different solvents. And you can even analyze the surface, how is the aggregation, the composition, the phase, the charge, the functionalization. But right now, you can even go even further. So you can check this type of properties, but thanks to the TM in the new devices coming, you can also understand the thermic stability of these materials, the catalytic properties, electrocatalytic, or in our case, as I will explain you a little bit, the photocatalytic behavior of these materials. So right now, to make in situ experiments inside of the TM, we have two different approaches. The first approach is what is called the environmental TM. Here you have a TM, and inside you can put gas, and you can prepare your sample for this specific holder, and you can perform the in situ characterization. And also, we have what is called lab on the chip, that they are specific holders that you can do, for example, catalytic gas experiments, liquid experiments, biasing, temperature plus biasing, etc. And this system, it has some advantage if you compare for the environmental TM, because first of all, you only need one TM. And the TMs, as you know, they are quite expensive. And also, for example, if you want to do some gas, the pressure that you can achieve with these holders is much, much higher than in the case on the environmental TM. So for which application can we use as well the in situ? So imagine you want to check the physical, mechanical, chemical properties, the thermodynamics, microstructure, so you can understand the nucleation process, how they start to grow, as I say, the catalytic, but also some mechanical process, or melting, how it's melting or changing, making some phase transformation, etc. This in situ can be applied to a lot of materials from a lot of fields in order to understand whatever you can imagine. So here in Barcelona right now, you can start to make, we have buy some in situ systems. And so what we can do here is we have this gas plus heating holder, as you say, to make catalytic reactions under gas to understand the kinetics. And you can also even achieve atomic resolution. So you can see how the atoms are dancing during the reaction process. We also had some new liquid holders plus biasing or heating that here you can try to simulate what is you are doing in an electrochemical cell with bulk materials inside of a TM. And we also have one holder together that it brings the biasing plus heating, and also you can do some cooling. So you can go from temperatures from minus 200 degrees up to 1000 degrees, studying your catalytic materials, and also applying some biasing to see the cycles, oxidation, reduction process, etc. As per all what was explaining already a little bit, so I will not go super in. This is the scheme of one of these holders. It's composed from one top chip, which you have a Windows, which is electrotransparent, an O-ring to save everything, and this bottom chip where you can drop here as well, your material. And you also have some individual represents tubing, so it will be one inlet and one outlet to put liquid or gases. So, but what is missing in the commercial, if you want to buy some of these holders, what is missing is a photocatalytic holder. And this is what also we are trying to develop in our task 5.2 to put all the knowledge together to also make possible the commercialization of these photocatalytic holders. For what? So I would like to show you different scientific papers explaining why it's so important this photocatalytic holder. The first paper I would like to show you is this one. You have here two publications were coming in 2021 and recently one in 2023. That is the effect of some system composed of nickel nanoparticles in a cerium oxide substrate that allows the CO2 reduction to produce methane. So this paper, this system was working that you have some solar light hitting the nickel nanoparticle, and this, thanks to this in photocatalytic reaction, the nickel nanoparticle start to increase their temperature due to the strong damped localized surface plasmods generated on this nickel nanoparticle. So as we don't, at that point, there was not the possibility to do a photocatalytic reaction with this photocatalytic holder specifically. What they did is they used in situ heating to reproduce this increment of the temperature. So thanks to this increment of the temperature, when you have in a reductive environment, using hydrogen plus CO2, so the hydrogen splits on the nickel surface, giving some protons, and on the interface, we produce the reduction from cerium 4 to cerium 3, the hydrogenation of the CO2 producing some carbonate, and then finally the reduction to methane, to obtain methane, and then thanks to this the cerium character of reducing oxidation, after the reduction of to obtain methane, the cerium 3 generated can oxidize again to perform to be again cerium 4. And it will be a really interesting paper to produce methane through CO2 methanization. So the second paper comes in 2023, and they were doing some in situ ILS experiments where you can understand better the reaction mechanism behind this process. So they make two types of experiments. The first one only applies heating temperature without hydrogen or without CO2 to see if we have some changes from CO4 to CO3, from cerium 4 to cerium 3. So this is one of these HADAF images from these materials, where in blue is depicted the cerium oxide and in red the nickel. And they were increasing the temperature from 120 degrees up to 400 degrees to see if there is this changes on the cerium. And the cerium in this case was completely stable in cerium for the state. So then they put this hydrogen and the CO2, and here we get already the reduction of this cerium. And you can see in figure 8 the line profile from the inside to the surface, where we get a decrement of cerium-4 and increment of cerium-3. And also in this HADAF image, you can see a bright light here showing the cerium-3, and here you don't have a bright light because it will be set up the nickel nanoparticle. So this was, again, a super interesting paper for CO2 reduction, but that we could not use a photocatalytic holder because it was not available. I tried to find on the literature some of examples showing what we can do on the TM, and I found that if you want to put light inside of the TM, you can have two different approaches. One through a sample holder, and the other through an existing port in the microscope column. So here they were doing some water splitting reaction using titanium oxide nanomaterials. And for this, they were using a kind of light fiber under a gas system because it was water vapor. So what happened is that you have a titanium oxide material, and thanks to this light and thanks to the gas, it was reducing to titanium-3 one or two layers from the anatase structure, making some amorphosization of the surface, making the reaction can then make it more that the reaction could occur, producing the water split. But this was in gas. And then I found another nice example to make more operando condition under liquid, that here they were trying to do exactly the same, but in this case for hydrogen evolution, where you have some titanium oxide, again, the nanomaterials in water, but in this case, liquid. And after applying some light, here you can see in dark, invisible, how the materials start to make this titanium-3 layer on the surface, making more favorable to happen the reaction and having some bubbles which confirm the hydrogen evolution reaction. And also they make some yield experiments to confirm this transition from titanium-4 to titanium-3. And this is one example, because I think a video always give you nice, when you see the things are better, it's easier to imagine. So I found one example from Dense Solution in collaboration with the Friedrich Institute, where they have some nickel oxide nanomaterial that first was reduced before a gas flow of helium, hydrogen, and oxygen with a specific pressure and using 330 degrees. So here it's this nanoparticle that at a specific time and a specific moment, it completely decomposes. And you can see now the importance of this in situ, because as you see this moment when the nanoparticles just break and decompose, it's maybe less than a second, but you still have to recover all the time the reaction. And to process data and to understand, because it was super fast, to understand the mechanism, we need to still develop data processing analysis. So to conclude, I would like to give you a small summary about in situ, that at the end, the advantage of making this in situ is that what I say initially in my first slide, that seeing is believing. So we can observe, we can quantify simultaneously the data to see all the changes in life. And it can be applied to several fields. But it also has some disadvantages. First of all, it has a tedious and complicated preparation processes where it's not easy and it's quite long. And we also have to take always aware from the artifacts, because, for example, the electron beam can make faster your reaction or can interact also with your material, producing some changes that later you have to be sure that what happened is to your catalytic or your cyclone and not to the electron beam. And with this, I would like to conclude. I hope I could give you a little bit the state of the art of this in situ, of what we want to do, and you like it as well. You enjoy these scientific papers that I showed. Thank you.